Hello, welcome to PhyzQuest. So in the previous video we have discussed about the differential operator associated with vector calculus like gradient, divergence and curl, etc. In this video we will discuss about the integral theorems associated with the vector calculus. So there are mainly three important theorems. First is the Gauss divergence theorem, second is the Stokes theorem, third is the Green's theorem. So now one thing you must remember that all these theorems originate from the fundamental theorems of the calculus. Now I am not going to mathematics of this. We will in this video will briefly discuss about each of the theorems and their application, and we'll try to understand all these theorems through practical example. Okay, so let's discuss them one by one. First is the Gauss divergence theorem. Now, as per the definition of the Gauss divergence theorem, it relates the volume integral of the divergence of a vector field to the surface integral of the vector field enclosing that volume. Now, if we write it down mathematically, suppose we have a vector field F. Therefore, mathematically, if we try to write down the Gauss divergence theorem, it will be integration over the volume V, divergence of vector field F will be equal to integration over a closed surface S, F dot ds. F is your vector field, as I already said. So now here this symbol, this enclosure symbol here, this indicates a closed surface. So this means here this volume V, this V is the volume of a three-dimensional region which is enclosed by a two-dimensional closed surface S. Now this is the mathematical expression. Now let's try to understand it practically. So to understand that, let's consider an example. Consider a container filled with certain gas. So now this represents a closed surface S enclosing a certain volume V of the gas. Now let us suppose the source of the gas is within the container. Suppose some kind of a pipe which is there inside the container. So through which gas is entering the container. Now when the gas is entering the container, suppose the container completely gets filled. Now after that, further filling up the container, it will lead to create an excess pressure within the container, and the container will try to expand, and what will happen is when the container will try to expand because of the excess of gas, the excess of gas will try to come out. So this will cause an outward flow of the gas in all direction through the surface S. And this outward flow of gas in all possible direction is the outward flux through the surface S. Therefore, the total gas which is coming out, we can say that this is equal to the total outward flux through the surface S. Now this gas which has come out as outward flux was supposed to be used in expanding the volume of the container. So therefore, this is equal to the total expansion of the gas within the container of volume V. So as you can understand clearly here, this expansion of the volume is same as the outward flux of the gas which is coming out, which is clearly same as the mathematical definition given in the Gauss divergence theorem. Now suppose you reverse the situation. Here we are talking about gas is coming out, that is outward flux. Now let's reverse the situation. Suppose here within the container we have a sink inside the container through which the gas is draining out. So now what will happen is, if the gas is try to drain out, then what will happen is the direction of the flow of the gas will be inwards. So that means the flux line will be inwards. That is, we can say it's a negative flux. So here Now what it will lead to is, it will lead to the compression of the gas. So that means the whatever flux lines, this is the inward flux, and the total gas which is getting compressed will be is the total inward flux through the surface S. And since this inward flux is getting a compression, that means the volume of the container is getting compressed here. Suppose you are considering a balloon, suppose. So obviously if the gas is draining out, the volume will compress. So in that scenario, what will happen is, this total inward flux through the surface S will be same as the total compression of the gas. So again, here the situation is reversed, but the definition remains the same. Only difference is here we are considering an inward flux. So again, we have understood that here the Gauss divergence theorem basically relates the volume integral through a surface integral, and we have understood this through a practical example. Now this is about the definition and the understanding the theorem. Now let's talk about some application of the Gauss divergence theorem. Now Gauss divergence theorem has many applications. Few of them, most important of them you can say, is in the field of electrostatic, which is the Gauss law of electrostatic. So Gauss law of electrostatic is basically shows you the electric flux. So here in terms of the use of Gauss divergence theorem in Gauss law of electrostatic is basically the conversion of the integral form to the differential form and vice versa. Now Gauss law has two type of forms, that is the integral form as well as the differential form. Now Gauss law of electrostatic is basically shows you the electric flux through a closed surface, which is represented as phi E, which is Q by epsilon 0. Q is your total charge. Now this is equal to integration over a closed surface E dot ds. This is your E is your electric field. So now this is a integral form. We have to convert it into a differential form. So for that we can use the Gauss divergence theorem. This is a surface integral. We can convert it easily to a volume integral term in using the Gauss divergence theorem. So this will be a volume integral over the divergence of the electric field E, that is del dot E. And right hand side, this will be epsilon 0 is a constant term. Q can be written as, in terms of volume integral, as Q is your total charge. So in terms of volume integral, it can be written as integration over of volume V rho into dV. Rho is your volume charge density. So when we write down both in terms of volume integral, by comparing both side terms, we can come out with differential form of the Gauss law of electrostatic, which is del dot E is equal to rho by epsilon 0. This is the differential form of the Gauss law, where rho is your volume charge density. Now in similar fashion, we have Gauss law of magnetostatics. It's very much similar. Only difference is electric field is replaced with magnetic field, and here the integration of the surface closed surface B dot ds, B is your magnetic field, this is equal to 0. Now this is a integral form, and this easily can be converted to a differential form, which is del dot B is equal to 0. So as you can see that in both the cases this Gauss law of divergence is clearly used by in conversion of the integral form to a differential form and vice versa. Now there are many other applications as well, but these are the main application. So now here we have discussed about the Gauss law and its application. In the next video we will discuss about the Green's theorem and the Stokes theorem.